Hi folks, this is your YouTube channel for witnessing the magic of mathematics and fluid dynamics. In today's video, I'll describe the real physics behind the term viscosity, which generally taught us in school, but this is not the correct version, or this is not the most generalized version. So in this video, we'll learn the real meaning of it. In school book, we used to say that the velocity gradient and the shear stress is proportional, and the constant between them is called viscosity, with this velocity profile in the image. Now, in today's video, we'll understand the viscosity in terms of the fluid particle deformation under shear stress and the velocity profile from bed to water table. Now, the viscosity is only manifested when the water or fluid is moving or is in dynamic condition. It is not manifested when the fluid is in static condition. Now, in the previous video of mine, I talked about the effect of boundary layer in a fluid, the formation of velocity gradient due to the messenger of momentum disturbance, which is viscosity, and the boundary layer thickness formation due to the momentum disturbance imposed by the solid boundary. Now, the boundary layer region and the velocity gradient tendency collides in open channel flow with each other and completes the flow profile. Now, in the very first theory of fluid comes with its distinction. As an example, if we apply a tangential shear stress to a solid, it gets definite deformation as you see in the first picture. It may gets equilibrium for particular shear deformation, may or may not come back to its original shape. That depends upon the property elasticity. But in case of fluid, it can't get back to its original shape as the deformation is happening continuously. Now, the constitutive equation or the property in fluid is the shear stress is not related to strain as like solid. In fluid, the shear stress is related to the rate of shear strain because of the continuous deformation, as it obeys the law of constitution as my laughing country. Now, you can see there is continuous deformation in the fluid particle. Now, imagine there is a one-dimensional parallel flow where the velocity is proportional to the height and also the shear stress is proportional to the height. Now, there is a fluid particle, I have pictured this here, which is just between the two adjacent layers of the flow profile. Now, the higher layer velocity is much higher. Then it tries to drag the lower layer with a shear force S. As the y increasing, the velocity is also increasing. So the higher velocity layer is trying to drag it with a tangential shear force. Now, according to Newton, there will be a shear stress developed around the velocity field, which is proportional to the velocity gradient. Now, in the deformation of fluid, we need to really understand this mathematically, look closely. The relative displacement of the point B in terms of A, which depends on the del theta, which is the angular deformation. And the relative displacement is del U into del T at a particular instantaneous time, where the tan del theta equal to del U into del T by del Y. Now, if the angle theta is really small, then tan theta equal to almost will be theta. Then we can have the second equation. If we apply the limit law here, where del t tends to 0 and the del y height difference is also tends to 0, then it forms du dy, which is directly the velocity gradient, and the limit of del t tends to 0, del theta by del t, which is the rate of angular deformation. Now, this is what is this? This is the mathematical significance of velocity gradient, du dy. Physically is not. We need to understand that in the kinematics of fluid flow, in a parallel one-dimensional fluid flow, where the velocity and shear stress both is increasing with the height, there one component of flow, the velocity gradient is directly equal to with the rate of the shear strain. Now, according to Newton, those are the Newtonian fluid like air, water and oil, where the shear stress and velocity gradient relationship is linear and the slope is viscosity. This is happen for a Newtonian fluid. And there are several Newtonian fluid like time dependent or time independent, where the linearity relationship between the shear stress and velocity gradient is changing continuously. We'll discuss about it in a later video. Now, the power law model, which is created by Sir Oswald, which is an extension of Newton law model, where he denotes the non-Newtonian fluid in this graph, where you can see it is addressed by this equation: shear stress proportional to m into du dy to the power n, where m is the behavior index of fluid and n is the consistency index of fluid. For n greater than 1, this is the curve you can see, which is for diluent fluid, and n lesser than 1, which is for pseudoplastic fluids. Now, the new non-Newtonian fluid example is blood, milk, polymer, ink. Now, there are some several topics which I can get it out of this video, which is, first off is viscoelastic fluid. If we apply the tangential stress and the fluid is still get back to its original shape after particular deformation, then it is called the viscoelastic fluid. We will discuss this in a separate video. And then the application of viscosity with few problems and with Navier-Stokes equation. If you like my work, please subscribe the channel. Thank you so much, and share and subscribe. Thank you.